So we have seen that there are these spectral transitions. Okay, so electron jumps from higher energy state to lower energy state and emits radiation. So we get spectral lines. Now all these transitions through all these levels are not possible. Okay, some are forbidden, some are allowed. That means there are some selection rules or some rules to be followed by these transitions. So if these rules are followed, then this transition is known as allowed, and if it is not followed, then the transition is forbidden. Okay, so there are some selection rules, some transition rules we can say. So what are these? Let's see. Before this, we have to know why we are using capital letters. Now in this case, in alkyl metals, we have only single electron, but when a system of electrons, that means let's say in valence shell there are 2 electrons or 3 electrons. So now let's consider 2 electrons. So their orbital angular momentum, their spin momentum, spin angular momentum. So these momentums interact with each other. Okay, with the nucleus magnetic moment. Okay, so all these things combine and make separate energy levels. So we have to combine capital S as S plus S1, S2 to S1 minus S2. Similarly, capital L, that is resultant of these two. Now in this case we have only one electron. So if we use capital or small, it's nearly same. But when we have more than one electron system, we have to calculate these like this. So for L, we will have small L1 plus L2 up to L1 minus L2. So these will be the values for capital A. For capital S, these will be the values. That is a resultant of spin angular momentum. This is resultant of all the orbital angular momentum. So now similarly for J, you have L plus S2, L minus S. So these will be the values for capital J. Now here it is 2 electron system. If there are 3 electron systems, then we have to add another one. So those calculations get very crowded. So now for our syllabus we have only one electron system, that is alkyl metals or alkyl metals. Okay. Now consider selection rule for capital L. So what is the selection rule for capital L? It is plus minus 1. That means it should change with value of plus minus 1. That means the transitions between only P and S, D and P, F and D, or P and D are allowed. Sorry, yes, P and D are allowed. That means plus or minus 1. The difference between capital L must be 1. Here, in this transition, you can see what is L value here. So capital L1, this is capital L2. So what is the difference between L1 minus L2? L1 minus L2 will be P has value of 1, S has value of 0, so it will be 1. So this is plus 1, our condition satisfied. Like this, we have delta J selection rule for capital J. It is plus or minus 1 and or 0. Similarly, for delta S, that means difference between initial levels spin angular momentum and final levels spin angular momentum. That is total spin angular momentum. The difference should be 0. That means if the S here, we can see here, what is the capital S value? As it is a doublet, it will be a half. So in the final state here, we can see here, what is the S value? It is half. So this half, what is their difference? 0. So we can say these type of transitions are allowed, and because they are following del S is equal to 0, this selection rule. Similarly, L, J and X, these are the selection rules, these are the main selection rules. Similarly, for small quantum numbers, we have selection rules. So those transitions which are following all these selection rules will go through a particular or a certain transition called allowed transition. Okay. Now del S, for del S we have plus minus 1, and for small magnetic orbital quantum numbers, del ML, we have plus or minus 1 and 0. These values are allowed. Similarly, for magnetic spin angular momentum quantum number ms, we have single 0. So these are the selection rules for any transition to takes place. If the transition or the states follow these rules, they are allowed. If it is not, then this transition is not allowed. So these are the selection rules. Here you can see del ms, we know the values. So minus 1, 0, 1, sorry, 1, minus 1. So these are the ML values, we know this. And for S, MS, we know it will be half or minus half. So this is upstream, it is downstream. You know this, okay? So this quantum number, this is our orbital angular momentum quantum number of individual electron, okay? And these are for total angular momentum of that electronic system or that atomic system. If there are more than one electron, total J value, that is total angular momentum quantum number, that is total spin angular momentum quantum number. This is orbital angular momentum quantum number for a single electron, okay? Single electron. If there are more than one, we will call it as L1, L2, okay? So like this. Intensity. So the rule is, when a transition occurs, then the spectral line is strongest in which the spectral line is strongest in which the J value and L value changes in the same way. That means what will be the delta J, it should be delta L. Okay, so they should change in the same way. Here we can see from this transition, it is delta L to what is the delta L? Here is 1, here is 0. So delta L is 1. Okay. What is delta J? We can see delta J is 0 because it is consider another spectral line, this transition from 2p 3 by 2, or we can say double A p 3 by 2 to double A as half. Now here we will calculate del L. So what is the difference in L? P to S, that is 1. But what is the difference between capital J value? Del J is 1. Now we can see here del L is equal to 1, del J is equal to 0, del L is equal to 1, del J is equal to 1. So in which case the L and J values are changing as same in this case, okay, not in this. So this is the less intense line and this is the strongest line. Now consider these transitions. Okay, this one. Here you can see for this line, this spectral line, we have what is the del L values? It is 1. Del J value, it is 1. For the next spectral line, this one, del L is 1, del J is also 1. Now, what is the next step in the rules for intensity? Whichever the line or whichever the transition has higher J value, that means this value or this value, largest J value, it will be a more intense line. So this line is more intense. Now there is another intensity rule for the intensity ratio. Now, how we will determine the intensity ratio? If we see this doublet, consider these two doublet half as half. Okay. So here we have these two lines. Okay, these two spectral lines. How we will find out their intensity ratio? Okay. For this we have the formula 2j plus 1. Okay. Here we can see These two spectral lines are arising from different levels and ending on a same level, okay, same common level. So we can calculate their intensity ratio with the help of this. Now here for first spectral line we can calculate 2j plus 1. J value we will take from here, okay, the not from the common level, okay, from here. So for this 2, what is the value of j is half plus 1. For this line, we will take j value 3 by 2. So 2 3 by 2 plus, so it is 2, is it? Yes, it is 4. So what is the ratio? 1 by 2. So this is how we will find out the intensity ratio for the double edge whose ending level is common. Now this same formula implies for let's say they are coming from same level, okay. Now they are coming from the same level and ending at different levels, okay, ending at different levels. Now we can use the same formula for obviously these will not be the notations, okay. Just consider these two spectral lines. They are starting from a common level, common energy state, okay, and ending at a different energy levels, okay. So this double edge we can find the energy, we can find the intensity ratio like this, 2j plus 1 in this single formula, okay. So if the spectral lines are arising from a common level and ending on different levels, we can calculate with this formula the intensity ratio. For the converse case, if the spectral lines are arising from a different energy levels and ending on common energy level, then we can calculate the intensity ratio with this formula also, okay. So this was the intensity rule, another intensity rule. We know nucleus and electron orbiting in this orbit. So this is electron. Now we know nucleus has its electric field. So due to this electric field, we know when there is electric field, there is a magnetic field. So magnetic field H. Now electron has also magnetic moment, that is spin magnetic moment. We can represent it here, that is mu as spin magnetic moment, okay, of electron. So electron is revolving like this. In this case, we have value of J L minus R. Okay, we can use capital letters or small letters. So another case, J is equal to L plus R. So this figure is for L minus R. Another one, same orbit, nucleus, electron, but now this time this spin is anti-parallel like this. Okay, sorry, spin has changed its direction. Now the magnetic moment, spin magnetic moment is anti-parallel to this H. Okay, in this case it is parallel, in this case it is anti-parallel. So in this case the mu S, that is spin magnetic moment, is parallel to the H value, that is magnetic field due to nucleus, and in this case it is anti-parallel, okay, to the H, that is magnetic field due to nucleus. This is spin magnetic moment due to the spin moment of electron. Now in this case this value is for J is equal to L minus half and this L plus half. So in this case, actually we have observed that this case is more stable, this state is more stable as compared to this, because here the spin magnetic moment and the magnetic field or magnetic moment due to the nucleus are parallel to each other, and in this case they are anti-parallel. So this state has more energy, it is unstable. This state has less energy, it is stable. For example, P, 2P, 3 by 2, 2P, 1 by 2. So this higher energy level. So this is more stable, this is less stable. Okay, so it has less energy, it has more energy. These are the two states. We can take this as an example. Here, electron and the magnetic field, the spin magnetic moment and the magnetic field due to the nucleus are parallel. In this case, the spin magnetic moment and the magnetic field due to the nucleus are anti-parallel. Hence, this energy is more. That is, it is not more stable. It is more stable with less energy. Okay. In this order, we arrange the energy states. Okay. This is normal order of doublet ion structures. The value with J plus 1 lies above, and the value with J L minus half is lies lower on the energy level diagram of doublets. Somewhere we may say we may see it is altered, but those are exceptional cases. This is general rule for normal order of